I hope everybody is doing well. So, ನಮ್ಮ last class we have covered a major chunk of magnetism part. So, moving charges and magnetism and the chapter part. We have also seen different types of questions based on, the chapter. Okay, so and all concepts and all different types of, numericals which are possible, as well as all the formulas, important formulas also we have covered. Now, positively, we are stepping forward with the next chapter, which is of great importance. So, we will be seeing that today. We are starting off with a new chapter for today, which is alternating current. So, let's see that. This is also a major chapter which needs to be, emphasized on. So, certain things are very important. So, we will be discussing all those important areas today. Okay. But that is what is planned for today. So, let me start sharing the screen. Just give me a minute. Yeah, I have started sharing. Just let me know if you're able to see it, children. I'm sharing the blackboard where I use it to write and explain Sringla. So I've started sharing it. So I hope you guys are able to see it now.
Yes, sir.
Yes. Okay. Great. So moving on with the chapter alternating current. Okay. Okay. Alternating current. So what do you mean by alternating current? So in the term, sometimes we would have definitely come across this term. Direct current, definitely we would have heard about. Alternating current is a different version, okay, a different version altogether. So what is the difference between, direct current, DC, AC அப்படின்னு சொல்லி கேள்விப்பட்டிருப்போம், isn't it? So what is the difference between AC and what is DC? So we'll try to have a basic idea between the different types of current that we have. Okay. So generally current na enna namakku ellarkume theriyum. We know what is current in general. Now we will try to understand what is alternating current and what is direct current. Okay. There is a very small, difference. That's it. Okay, which you need to be knowing with respect to this. So we'll see. Okay, in this chapter, alternating current is basically the current which is going to vary with time. It's time variant. சரிங்களா? It keeps varying with time. But when you talk about direct current, that does not vary with time. It is time invariant. That means it is constant with time. Its magnitude does not change with time. Okay, it is the same. If I say 2 volt DC, I mean a 2 ampere DC and a 2 volt DC அப்படின்னு சொன்னேன் அப்படின்னா, that means that current is basically having the same magnitude. 2 amperes only it is. At the entire time duration, if you say for 2 hours, for 3 hours, whatever it might be, okay, the magnitude of that current is going to be the same. But if I am going to say alternating current, 5 amperes or 2 amperes alternating current, you have to understand that its magnitude is going to change with respect to time. Now, how does it change? That is what we are going to see. It is going to change sinusoidally. So, sinusoidal function is basically used to represent an alternating current. Okay, so basic idea of alternating current as what I've given you. So now we will see it. We'll go through it. So alternating current is basically whose magnitude changes. Okay, so the magnitude changes continuously with time. We can say the magnitude changes continuously with time. And the direction is also going to reverse. And direction reverses periodically. And the direction reverses periodically. So this is the basic idea. So alternating current is one whose magnitude will change continuously with time and its direction is going to reverse periodically. So we'll try to show the waveform, how the waveform is going to look for both alternating as well as direct current. So to draw a compare and contrast, so I'm drawing a waveform. Okay, the waveform that I'm going to draw here, first on the top I'll show you. This waveform is basically, for the direct current. On the top you can see I have drawn a green line on the top. So that is parallel to the time axis. You can see it is not changing with time, right? With time it is going to be constant. At any point you choose, its value or its magnitude is going to be same. It does not change. So this is DC. But if I'm going to talk about AC, which is alternating current, it is going to be pretty different. Now, its magnitude we are seeing is going to change with time. And then I also told you it is varying sinusoidally. So this is how the graph will look. It is a sinusoidal curve. Okay, you can see its value changes. Now, as its value is going to change, so you can see that there are two peaks. One is a positive peak, and one more is going to be a negative peak. So there are two peak values that the current is going to have. Okay, so we call this as positive peak on the top. Let me call it as plus I naught, and at the bottom we can say it is minus I naught. So these are peak values of the alternating current. You can see that it is reversing in its direction. First, it is a positive half cycle, and then it is a negative half cycle. It is reversing. So you can see these are the two aspects that you need to keep in mind for both your alternating current as well as your direct current. Okay, so that's the basic idea as far as the alternating current and direct current are concerned. So now you have understood the subtle difference. Now we are going ahead. How do we are going to now represent? What is the representation of alternating current? How can we express it or how can we represent it? Is what we are going to see. Okay, so we can write it as we can express, or I'll say AC alternating current is expressed as okay, it is expressed as now we can say it as V is equal to V naught sine omega t. Now for alternating current, we express the voltage. The relationship is given like this. Same way, the current relationship, if I say current, how do I express current? Now let us see that also. Okay. Before we see the current expression, now in this expression, V, what is V? What is V naught? What is omega? What is T? We need to understand each and every term individually. Okay. So here, your V naught term is going to represent peak voltage, peak or maximum value of AC voltage, the alternating current voltage. Okay, and omega is nothing but your frequency. It is the angular frequency. Okay, angular frequency, usually it is in radians per second. Time is nothing but the instantaneous time. T represents instantaneous time. And V is going to represent this V on the left hand side, on the LHS side, is going to represent the voltage. This is the, it's not peak voltage, this is just the instantaneous voltage. It is the instantaneous voltage. So these are the different terms that you will have to know for an alternating current when you write the expression in terms of voltage. That is V is equal to V naught sine omega t. What is each and every term? Okay. Same way, now I want to write the expression for current. Okay. From Ohm's law, we all know what is current, isn't it? So from Ohm's law, you know that current I, how can you express? You can express it as the ratio of potential difference and resistance, isn't it? We can write I as V upon R. Yeah, general expression. So what is what about your V? If you go for a rearrangement, you can simply say V is equal to I times R. Simple. Okay. This is your Ohm's law relationship. Same way, if you're going to write for peak voltage, you can write V naught is equal to I naught into R. In terms of peak voltage, this expression can be written. Now go and substitute these values in the first expression. Okay, let me mark the first one as equation 1. If you go and substitute these values, say this is 2. If I put values of 2 in 1, what am I going to get? I will get expression in terms of current. So what will be the expression? I can say I naught into R is the term for V naught. V is nothing but simply I into R. So I into R is equal to I naught into R times sine omega t. So you can see R terms will get cancelled off, and finally you can write I is equal to I naught sine omega t. Simple. So you can write it like this, isn't it? So this is how you can write the expression for the alternating current in terms of the current terms. This is how you write. Okay. So these are the two major expressions that you will have to, understand and keep it in mind. Okay. So alternating voltage, how to write, and alternating current, how to express it. So these are the two basic expressions. Okay. So here in the second expression for current, I is going to represent instantaneous value of current. It is the instantaneous value. Instantaneous current. And I naught is peak current or maximum current. Okay, peak or maximum current. The other terms you know it. Omega is angular frequency and T is instantaneous time. Okay. So these are the two important aspects that we have seen so far. How to express the values of alternating current and alternating voltage. We have seen both of them now. Okay. Now moving on. How can we write time period? What is time period? How to express time period? Okay. Time period is given by capital T. So here you need to understand how to express time period in terms of angular frequency, that is omega. Okay. So there is a relationship then omega is equal to 2 pi into f. This is the relation that we will be using. Now here you can see omega is angular frequency, f is linear frequency. Okay, you need to understand that there is a difference between both. Omega is the angular frequency, that because the waveform is sinusoidally it is changing, so the frequency is basically angular, but small f here represents the linear frequency. It has to do with the time. Okay, it has to do with the time period. So frequency can also be expressed as the reciprocal of time period. You all know it. F is 1 upon t. You go and substitute here. So what happens if you go and substitute this relation above? F is equal to 1 upon t. What do you ultimately get? You will get the relation as omega is equal to, yes, what is the relation? You will get 2 pi upon t, isn't it? This is what we get, which ultimately tells us that time period is 2 pi by omega. So this is the expression for time period. So if you know the angular frequency of the waveform, you can calculate the time period by using this relation. Okay, so this is the time period. Okay, so when I take one waveform, okay, now I'll show you when you express a waveform or when you try to draw a waveform, a sinusoidal waveform. So I'm showing it here. This is a sinusoidal waveform. What is time period T? Where does it come into picture? The wave starts from here. Say at this point, time is 0. At this point, it is half of the time. So because only one half of the wave is complete, so the time period is written as t upon 2. And at this end, completely it is full, the wave is complete, so time period is t. So the time taken to complete one full waveform, that is positive half cycle and negative half cycle, together, that duration is your time period. Okay. So here, if I'm going to divide this again into two parts, at this part, it is going to be t upon 4, 1/4 of the time period. And what about at this part? 3/4, right? So it is 3t by 4. Okay. So like this, we can express the time period for different portions of the wave. Okay. So this is something that you will have to understand. So for a waveform, how the time period you are going to mark, which is half time period, which is one full time period, which is 1/4 time period, and which is 3/4 time period. So this idea has to be there. Okay, so this is all about the time period of the waveform, sinusoidal waveform. Okay, so this is now, I hope it is clear. Now we are moving on to write down the expressions. So how to write down the expressions? Okay, further we will see. Okay, with that we will proceed further. It is quite simple only. Okay. So So moving on to the next part. Yeah. So now, children, we are going to now discuss what is the average value of alternating current over one complete cycle. So first thing, we are going to discuss the important aspects of the waveform. Let me just put in pointers. So first pointer, we are going to discuss what is the average value. Okay, the average value of alternating current over one complete cycle. What is its average value? Okay. Now, because the derivation aspect is not there for us, I am directly going to give you the relations. Okay. There is a derivation for this, but it is not necessary for us. So I will give you the direct relationship. What relation is used to calculate the average value? I am giving you the direct relation. Okay. For one cycle, when I say that is one complete waveform, so therefore you need to understand that the time period is for one complete waveform is from 0 to t. Okay, so we say it is from 0 to t. Now, when you're going to find out for one full waveform, the average value, always keep in mind for one waveform, the positive half and then the negative half, they will cancel out and totally it is going to be zero when you go for average. So for the average value of current, AC current for one full cycle is always zero. So I average is zero in this case. Okay. So whenever they ask you the average value of AC over complete cycle, it is undoubtedly it is going to be zero. But when you say half cycle, things would take a different turn. In that case, not necessarily it will not be zero. In that case, what will you do? That also I will tell you. So other than one complete cycle, if they are going to ask, say for half cycle, please use this relationship. We will use the relationship as okay, I average, okay, is equal to. So there is a simple term which you have. We are going for integration. So it is represented as an integral, integral of I naught into sine omega t into dt. This is the expression. Now, when I say complete cycle, what would be my limits? It will be from 0 to t. Okay, this only I told it is 0. When you integrate this, you will get 0. But if I say half cycle, okay, then instead of t, I would put t upon 2. That's it. Okay, I will not take one complete cycle. I will put t upon 2 and then I will proceed. Okay, as simple as that. So we take t upon 2 and then we proceed. Fine. So then you will get a corresponding value as your answer. Fine. So I will, for simplicity, I'll show it to you, for one step so that you will be able to implement it in case you want to find out for half of the cycle or say one fourth of the cycle. Okay, what is the current value? What is the I average for one cycle? It is zero. For half, again you must do the integration. For one fourth, you will take t by four and you will do three fourths, three t by four and you will do.
நான் தான் பேசினேன்.
That's it. The limits only will
அதான்
change.
நாளைக்கு காலையில்
That's all. Okay. Otherwise, the steps would remain the same.
காலையில்
Okay. Now
பணப்பாளையத்துலேருந்து
I'll show it to you how we generally
ஈவினிங்
do it.
வரும்போது
Okay.
சிவாநகர் வரும். சரியா?
So I hope you guys would have the basic idea
குமாரிலேருந்து
of
கூப்பிட்டு வருவான்.
integration.
அவன் அவன்
Okay, I
குமாரிலேருந்து வர
suppose. Can
சொன்னான்.
you understand integration, everybody?
இந்த சரி இந்த சரி
You
நாங்கள்
have the
ஈவினிங்
basic
வரும்போது
knowledge of
அப்பா அம்மா
integration.
அங்கே புது வீட்டில் இருக்காங்களா உங்கள் வீட்லையா?
So shall I show it?
புது வீட்லையா? அப்போ அங்கே அங்கே போயிட்டு அப்புறம் சிவாநகர் வரும்.
Yes, sir.
Yeah.
ஈவினிங் வரும்போது
Oh,
எப்படியும்
okay,
ஒரு 6
fine.
மணிக்கு மேலே வரும்னு
Great.
நினைக்கிறேன்.
Okay, so we'll go slow.
ஓகே
You need
ரைட்.
not worry. Okay,
அவன் வந்து
it's
இங்கே
quite simple
போகிறான்
only. If you have the hang of it, it is
கவிஷ்
definitely going to be
கவினா
easy. All right. So this integration is nothing but it's a
ஓ தேர்ஸ்டே
part in
போயிருக்கானா
calculus,
சரி சரி ஓகே
where you go,
ரைட்
you're adding up term. Integrate means to just add up. Okay, you take a small strip and you just add entire thing, you get the area, you can find out. So that is what is the basic idea of integration. Okay, so now we are moving on. So when you try to integrate such terms, always you need to keep in mind, okay, what are the constant terms in your integration, expression. For example, if this is my expression, integration from say 0, okay, 0 to say this time I will do it for t by 2. Okay, 0 to t by 2. I naught sine omega t into dt. Okay. Now, children, here you need to understand this dt is there, no? This is called the integrating factor. Okay, it's a factor of integration. So we will call it IF. IF stands for integrating factor. Apart from that, what else is left? Whatever is there, apart from that, inside your integration sign, you call it as the integrand. Okay, you call it the integrand. So integrand is something that needs to be integrated. An integrating factor is basically the term, it's a variable term that tells you which corresponding variable is integrated. So when I say dt, you can see it's a small t only which comes into picture. Now that small t is only appearing in sine omega t. For I naught, you don't have t at all. Okay, are you understanding? So that constant, you can take it out of the integration sign. Okay, so here the constant, which is the constant term? The constant term is I naught. So I will take this I naught outside the integration sign, so that will come out. Okay, so we can write this as I naught integration. The limits are from 0 to t by 2 sine omega t into dt. Simple. So we will express it like this. Next, you have to know the formula. What is the formula for integration of sine omega t into dt? It is of the form sine ax into dx. Okay, we will use that formula. Does anybody know the formula by any chance? You can tell me. Okay, so integration of sine ax into dx. The formula for integration of sine ax into dx is minus cos omega x. Okay, but here I don't have x, we have t, so I have to change it. Okay, so minus cos omega t divided by omega. Okay, this is the formula. Again, I am taking the brackets because still the limits I have not applied. So the limits are from 0 to t by 2. Okay, this is the next step. Again, further, here we are going, and now we are going to substitute the corresponding values. Okay, we will try to substitute the values. Now, before you substitute the values, here, now you need to understand that t by 2 where to substitute. Yes, t by 2 we will substitute only for that small t. Can you see the small t expression? That is only the function where you are going to substitute. That is the variable, sorry. So that is where you will substitute. Okay, so it is usually upper limit minus lower limit. But what is omega? Omega is also having some meaning, right? I taught you. Omega is expressed as, how do you write? The angular frequency in terms of time period. Just now I told you. Omega can be written as 2 pi by t, isn't it? So please keep that in mind. So we can write it as 2 pi by t. First you substitute that. So I naught times within brackets minus cos omega is 2 pi upon capital T into small t. Okay, let it be there. Divided by this down also there is another omega. That is also 2 pi by t only. Close the bracket. I am only substituting for omega in this step. So the limits are from 0 to t by 2. Then you can see, children, the term in the denominator that gets reciprocal and can also be extracted out. Okay. So when you extract that out, so how would you write it? So it becomes I naught into t divided by 2 pi. Okay. Minus sign is there. Don't forget. So I'm putting the minus sign here. This is minus. Now, the term inside what I'm left with is cos 2 pi. Now 2 pi by t, that is there as usual. Now I'm going to substitute my limits. You see, first always upper limit, then only you will substitute lower limit. Upper limit minus lower limit. The upper limit here is t by 2, isn't it? So t by 2. So I'm substituting the place of t only I have substituted, small t by 2. Upper limit minus, now coming to the lower limit. What is the lower limit? It is 0, right? So what is the value of cos 0? Anybody? Because t is 0. 0 into 2 pi by t is 0. So it is cos 0. Cos 0 value is 1. I hope you all know it, right? It is 1. So that becomes 1. Fine? That's it. Now in this term, you can see the t terms get cancelled out. I can also cancel out this 2 and 2. It's all the angle only. It is entire. This is entirely common for the cos. Keep it in mind. It's the entire term. Okay. So TP I will cancel. So I'm left with cos pi inside. Okay. Finally, what am I going to get? I will get minus I naught T upon 2 pi. The next step. So within brackets, cos pi minus 1. This is what I get. What is the value of cos pi? Cos pi has got a value. Anybody? Is it plus 1 or minus 1? You must be knowing it. It comes in trigonometric functions.
-1, sir.
Yeah. So cos pi value is basically minus 1. That's correct. So when I put minus 1, what will happen inside the bracket? Minus 1 is minus 2. That minus into minus becomes plus. So the final answer is 2 I naught into t divided by 2 pi. 2 cancel. Final expression I naught into t divided by pi. So that is the final answer. So the average value of current for half cycle, okay, the average value of the AC current for half cycle is how much? It is nothing but I naught into t upon pi. By integration only you can find out. Same thing if now they ask for 3/4, again integrate. Limits will change from 0 to 3t by 4. If it is for 1/4, 0 to t by 4. That's it, children. Otherwise, the steps will remain the same. Okay, this is the method. This is the procedure to find out. Is it clear? So this is how we do it. That's the reason I'm going slow. Okay, this is a crucial area where you will have to understand how to proceed with the steps. Now, there are questions where they can ask you what is the average value. They will give you the time, period value also. That is, say for one time period is 10 seconds, 15 seconds, that they can give. So first you will calculate this average value and then you will substitute in the place of t, whatever is the value given as per the question. And then you will find out the answer. That is how you are supposed to do. Okay. So this is all about it, children, for the average value of the AC current. Whether it is for full cycle, half cycle, or 3/4 or 1/4, this is the method you will proceed and you will do. For full cycle, keep in mind it is 0. Okay, you may not calculate and even if you calculate, you will get 0. That's a different aspect. So it is 0. Okay, that is the small tip that you can keep in mind. It is non-zero for others except for one full cycle. So now we are moving on. We are done with the average value. Now we are moving on to the mean value of alternating current. Okay, so we will see what is the mean value of the current. That is the AC. Okay, so mean value again very similar. It is also called as average. Okay, so mean value of current we say again we do it the same way only. Okay, integration I naught sine omega t, whatever it is, you do it the same way. Okay, so I'm giving you the direct expression here. So the mean value can be expressed as I mean or say I average. Okay, now this depends. For this I'm telling for the half cycle. Okay, half cycle what we have done already we have calculated here. Above we have calculated and we have kept ready made. So what is the value, mean value for half cycle? If you say, so I naught by I naught into t by pi. So that is the corresponding value we have calculated. So that 1 by pi, you can express that in terms of, even decimals also. So please keep this in mind. I'll give you the direct value for the, mean or the average. It can be expressed for half cycle as 0 point. In decimals itself, I give instead of fraction, decimal is better. 0.637 I naught. This is the average value of AC over the first half cycle. Okay, this value. So you can directly substitute and you can find out. Provided peak current value is given, you can directly compute the average value of current over the first half cycle. So average value of AC over first half cycle. For that, this is the value that you will have to keep in mind. Okay, same way, average value of voltage. we will write instead of I, you will put V average. Okay, V average is equal to again the same thing 0.637 P naught. That's it. This is how you express the V average. Okay, average value of the AC voltage. Again for the first half cycle only. Okay. First one is for the expression for current, second one is the average expression for voltage. So these are the values. So directly you can substitute your peak and voltage and peak current and you can directly compute the average values in one go if it is for first half cycle, if it is for the half cycle. Okay, that's it children. Then we are moving on to the next part. Then we have the root mean squared value. It is also called as RMS value. RMS stands for root mean square. Okay, root mean square value. Okay, root mean square value of AC. What is the root mean square value of the AC? This also, now here the root mean squared value means what is the meaning? We define this particular term, root mean squared value, as the value of the current which is going to reduce the heating effect in the resistor when it is going to be connected to a AC supply. Whenever you have a resistive component connected to the AC supply, so it is going to there is going to be a heating effect that it experiences. So that current that is involved during that process, we call it as the root mean squared value, sometimes also called as virtual value of AC. So therefore, this value is given by RMS means. So IRMS is expressed as I naught upon root 2. Okay. So IRMS is nothing but I naught upon root 2. So again 1 upon root 2 when you go on substitute becomes 0.707 I naught. Okay. So this is how this is the general formula for IRMS. That is the root mean squared value of current. So we express it like this. So again, what is the root mean squared value? It is basically the steady value of current which produces the heating effect in an electrical component such as a resistor when alternating current passes through it. Now, in our day-to-day life, we are definitely seeing heating effect in our the electric appliances and electric gadgets that we are using. Right from our television sets to our electric water heaters to the devices that we are using, even our smartphones, right? Whenever you charge it, don't you see that it's getting heated up after some time? Now we wonder why it gets heated, right? So that is because there are components in our device in the devices that we are using that gets heated up because the AC current is being used, okay, and it is going to cause the heating effect. Now, whenever I say AC current is being used, please keep in mind only when AC current is being used in the device, there should be a heating effect, not for DC current. Okay. Now coming to the mobile phones. Now mobile phones, when you put them for charge, say 10-15 minutes after charging, you can see it gets heated up. Okay. Now is it getting heated up because of alternating current, or is it getting heated up because of direct current? So this is something that you will have to know, right? Can anybody tell me what current is our device is using? Our mobile phone, mobile, and the gadgets, be it your earpods, okay, your headphones when you put it for charging, wireless. What is the current that it is utilizing? Is it the IRMS current that is entering inside and producing the heating effect? Yes? Anybody? What type of current do our devices use in our homes? Is it alternating current or direct current? It's okay. You can go for a guess.
Alternating current.
Alternating current. Okay. Partially you're right, but it's actually different. Alternating current is when you plug in children. We think that alternating current only is entering inside and going, but you seen your mobile phone and laptop have got big adapters. These adapters have a circuit inside. Okay, so alternating current Yes, that is the supply, which we are getting to our homes. But are we really using that for charging the mobile phone? It's only for mobiles. It does not apply for all the devices, only selective devices. There is an adapter. Now, have you wondered why do we have an adapter? The adapter is there because it is going to convert your alternating current into a direct current. And then it is only utilizing. Why it is converting? Because the mobile phones are specialized to function based on direct current. Okay, they can only operate on direct current. That's the reason you will have to use proper adapters and then charge your mobile phones. Otherwise, it would go for a toss. Okay, so it converts. There is a converter. What is that converter? We will be learning. It is called as a rectifier, children. There is a rectifier that is present that rectifies the alternating current, and it will send it as a direct output. AC input will go as a DC output as it comes out from the adapter and then charges your mobile. So that is what is happening. Okay. So it's not really the alternating current that is going to produce the heating effect in your mobile. The DC current is responsible to produce the heating effect. Even though your supply is going to be AC, there is a conversion from AC to DC happening in the adapter. Okay, this is something that you will have to keep in mind. All right. So like this, so most of the electronic items that we are using, are going to function in a DC. Not everything, most. Certain things are they function on AC itself. There are exceptions, but not all, but many of them. That is what we need to understand. Okay, so this is the relationship between RMS value and peak value of current. So RMS and peak value are just related by a factor of root 2. That is the only difference. So IRMS is I naught upon root 2. So this is how you need to understand what is the relation between both the currents, peak current and RMS current. Okay, that's it. And there is also something called as the heating effect. So what is the amount of heat we are going to ask? So there is the heat that is being produced is given by, so I will say, heating effect of the current is given by the Joule's law of heating, which tells you that H is equal to I square R into T. This is the general expression. Okay. General expression for heating effect is H is equal to I square R into T, where I is your current, R is the resistor, and T is nothing but the instantaneous time period. Okay. Same thing now when I'm going to express in terms of, say, potential. So that is the potential difference. Appropriately, it is going to change. Okay. So in terms of potential, you guys know you will go and substitute in the place of I. You would substitute. I is equal to V upon R, right? Because V is equal to IR, I is equal to V upon R. So you go for a rearrangement. Again, Ohm's law, you use it and you rearrange. I is equal to V upon R. You go and substitute that. So then the heat is given by the expression E is equal to V square times T upon R. This is what you get. Okay. So this is the expression that you are going to get for in terms of voltage or potential difference. Simple. So appropriately in the place of I, if I go and substitute, in terms of RMS current, yes, of course you can substitute. It can be I RMS square R into T, okay, or it can be V RMS square times T upon R. That depends based on whatever current you are talking about. But this is the general expression for heat. What is the unit of heat? You all know it is joules. So the unit for both of them, okay, the unit of heat is joules. Okay, both of them it is going to be in joules only. Okay, so that is the basic unit that needs to be kept in mind. Okay, otherwise it's just a simple thing, right? So this is the basic aspects. Now we have seen the different the expressions for current and voltage, the general expressions. We also learned the average value, and we have learned what is the RMS value, the relation between RMS and peak value, and heating effect of current. Okay, and how the periodic waveform is expressed. All that we have seen. Okay, now based on that, we will see certain questions. We will see the simpler ones first. Okay, here comes the first question. So we'll see the practice questions now. without further delay. So the first question, children, here on the screen. Okay. So the question is, okay, the peak value, peak value of an alternating current, of an alternating voltage, we'll put it that way, of an alternating voltage applied applied to a 50 ohms resistor, 50 ohms resistor is 10 volts. Okay, is 10 volts. The RMS current, okay, the RMS current when the frequency is 100 hertz, when the frequency is 100 hertz is the frequency is 100 hertz is, I'm giving you the options. Option A, it is 131.3 amperes. Option B, 141.4 amperes. Option C, 232.3 amperes. And option D, 132.6 amperes. Okay, these are the options. So the question is, they have given you the peak value of alternating voltage applied to a 50 ohm resistor is 10 volt. They have given you that. They are asking you the RMS current when frequency is 100 hertz. Okay. So to find out the RMS current, first you should know what is the peak current. Obviously. So find the peak current and then find out what is the RMS current. That's it. Okay. So anybody, can you tell me the answer for this? So what is given in the question? Please write that first. What is the given data? In the question, they have given you voltage, right? What voltage? Again, peak voltage, which is V naught. So V naught is equal to 10 volts. Okay, that is given. Apart from that, you also have the resistor. Resistance. Resistance is 50 ohms. Apart from that, frequency. They have given you the frequency. Here, linear frequency. How much is that? 100 hertz. Okay. These are the given parameters, right? So what is the, how can we find out I naught? Because only if you find I naught will you be able to find IRMS, right? So I naught, what is the relationship?
V naught by R.
Yeah, you will use V naught by R. That's it. So which is nothing but 10 upon 50. So 10 upon 50 is again 1 upon 5. Keep it like this only, 1 upon 5 amperes. Okay, once you have found 1 upon 5 amperes, now you can go and find out what is IRMS. What is the relation? I gave you a direct formula in terms of decimal, if you can remember. IRMS is 0.707 times I naught, isn't it? Directly use the formula. Substitute. So what are you getting? 0.707 times 1 upon 5. Okay. Cancel out that 5. So cancel out. How much are you getting if you do the simplification? 0.707 upon 5, which is 707 upon 5,000. Go for a cancellation.
Option B, sir.
How much?
Sir,
These
option B.
values, these values are all in milliamperes. I gave it as amperes. My bad. It is in milliamperes. They have given it in within brackets. All are in milliamperes. So option B only, right? Okay, correct. So you will actually get that is 141 if I'm going to write in this format. 141.4 into 10 power minus 3. Is that right? You will get it like that, isn't it? Into 10 power minus 3. So that is what? Milliamperes. Fine. So the options are actually in milliamperes. So everywhere there are milliamperes. So answer is option B in this case. Okay. Great. Now going on to a different model. One more model we'll see. The second question. Question number 2. Okay. So the next question. The RMS value of the alternating current depicted below is. Okay. What is the RMS value of the alternating current that is depicted below? So you have basically there is a graph, there is a waveform. So they are asking what is the RMS value. Okay, this is the waveform. So here you know this axis is current axis. The vertical axis is always current axis, and the horizontal axis is always the time axis. Okay. Now this is how the graph looks. This is the graph. The values are here it is 0, and on the top it is peak value is at 2 amperes, the positive peak, and negative peak is at minus 2 amperes. Okay, this is the graph. The question is you will have to find out what is the RMS value. Okay, options. I'm giving you the options. Option A, 1 ampere. Option B, 3 amperes. Option C, 6 amperes. And option D, 2 amperes. Okay, what is the RMS value of the AC current that is depicted below? That is based on the graphical data you should find out. Okay. RMS stands for root mean square value. Okay. Yes,
Sir, 1 ampere, sir.
1 ampere,
sir.
Okay, why is it 1 ampere? How did you calculate? It's not 1 ampere actually.
Sir, I not equal to 2A, sir.
I naught is equal to 2A. No, when did I teach you that relationship? Is I naught equal to 2A? Or root 2A? Root 2 times I naught, like that you're telling? I naught is root 2 into IRMS. That is okay. Okay. So here you have information about that, isn't it? So how can we find out what is the RMS value? Whenever you have a graph, you will have to be very careful. See how many cycles are there, positive half cycle, negative half cycle, everything. Everything needs to be taken into consideration. Okay. Now always keep this in mind. Whenever you have graphical questions and they are asking you IRMS is root mean squared value of your current. Root mean squared means first put the root. Then how many portions are there? One is positive half. Then you have one negative half. Then one more positive half, isn't it? So positive half, what is the value? Peak value. So we can say that is I1. Okay, I1 square. Plus negative half, I will call it I2 square. Plus next third positive half is there. Let me call it I3 square divided by 3. This is what is root mean squared value. Whenever you have a graph, please keep this in mind. So you have to understand that there is a positive half, negative, and positive. 3 things are there. Okay. So therefore positive, that is I1 I have taken. Then second part, negative, I have taken it as I2. Then third, positive again I3. Then you will go and substitute. Okay. Now you substitute the values. What will be your answer now? It's totally different. So what is I1? I1 is 2 amperes, isn't it? Positive half, 2 amperes. So 2 the whole square. What is I2? It has gone to the negative peak, minus 2. So I will put minus 2 the whole square. Plus I3, again positive 2, positive half. So plus 2 the whole square divided by 3. Okay. You simplify all this. How much you will get? Don't you think the answer is going to be 2? Isn't it? Ultimately, you get the answer as 2 amperes. Actually, the answer is 2 amperes. Option D is the answer. So whenever you have questions like this, you should be very careful about this. So never go with the direct formula, which is you have to interpret from the graph only. It is graphical interpretation is like this. Whenever you have numerical interpretation, that is totally different. So there are two different ways of approaching the competitive questions. Please keep in mind, especially for alternating current, whenever you have questions like this, okay, graphical interpretation of IR, root mean squared value of current or voltage is totally different, and the numerical interpretation is totally different. Please don't mix with both. Don't get confused with both of them. Okay, there are two aspects of solving. That's the reason I brought this question into, I introduced this question, okay, for solving. Is it clear? So this is how you do the solution for graphical based questions. Okay. Graphical based questions, it can be any type of function, not necessarily a sinusoidal function. Now, what type of function is given here in the graph? The way you are seeing, if you can see itself, you can identify. It is a square wave function. It can be a square wave function. It can be a sinusoidal function. Okay. It can be a sawtooth function. Whatever function it is, the method and the approach is the same. Okay, this is how you will do. Average means root means squared, under root. You will add them. You look at how many peaks are appearing, and based on that, you will divide and you will square it, and then you will simplify and get the answer. This is the approach for graphical based questions. I again repeat, numerical based questions. Then you will use the formula that I have taught previously. Okay, that is a numerical approach. Fine. So with that, we move on. So this is how you do it for this type of questions. Okay, graphical based questions. Fine. Now we will see another question based on a different model. Third question. Okay, question number 3. So here is the question. The or we can say current flowing in a circuit. Current flowing in a circuit is modeled. Current flowing in a circuit is modeled by the following expression. Current flowing in a circuit is modeled by the following expression. That is, I is equal to I naught times T upon tau. This is tau. You remember torque. Okay, that symbol, Greek symbol of time is tau, so which we use for torque. Okay, I is equal to I naught times T upon tau. For okay, I'll change the color. Let me just go back. Okay, T upon tau for a specific time. For a specific time. The RMS value of current, the RMS value of the current between the time period, T is equal to 0 to T is equal to tau is given by now the options. First option A, the first one, which is I naught first option I naught into root 2. Option B, I naught upon root 2. Option C, I naught into root 3. Option D, I naught upon root 2. These are the four options. Now here they have given you a function. The question itself is based on the function. Okay, they are modeling a function as I is equal to I naught times t by tau. The question is you have to find out what is the RMS value of current between the time period t is equal to 0 to t is equal to tau.
Sir, option A, sir.
Option A, I naught into root 2. Are you sure? Okay, fine. So, okay, so you have tried something good, but actually the answer is different. Okay, answer is option D. It's okay. This is a higher level question. Okay, so we'll see how to approach such questions. Now, whenever they tell you time period, I will give you a small tip. Okay, to keep in mind. Whenever they are giving you a time period, and when they are giving you a question where there is a function, whenever you have a mathematical function, please understand you have to do calculus. Without calculus, you will not get the answer. This you have to keep it in your mind. Direct method is not possible for this question. Now, when I gave you the concepts, can you recall where did we come across calculus? At one part, I also did the calculus and showed. Can you recall? Right? So we did the calculus and we approached at a final result. You guys remember? That approach only has to be followed for such questions. Whenever you have a mathematical, expression, whenever they say modeled by, or there is an expression given by, whenever they say this, you need to understand that you will have to go for calculus, either differentiation or integration. Out of these two, one thing has to be definitely done because they are specifying the limits here from 0 to tau. Okay, so this is important. So therefore, we need to do that. Okay. Now coming back, so we'll try to, approach this using a calculus approach. So again, so when you try to do this here, so when I'm going to substitute and when I'm going to integrate, again here root mean squared value, first average value, you try to find out. Okay, so I'm trying to write down. First, I will write the expression, and then we will go for the calculus approach. First, we are writing the expression. What is it? I is equal to I naught. The question is this. The expression is this. I equals I naught times t upon tau. This is what we had, right? This is the expression. Now, whenever expression like this is given, now you try to substitute, do the calculus approach. So find out what is the root mean squared value. So whenever we say root mean squared value or IRMS value, so you need to understand that IRMS can be expressed as under root mean squared. Mean, I mean, so whole square, yes. So that squared value is what we want. So that is a squared expression for a given function. So we express this. First, we want to find out what is that mean value. So I mean the whole square. So this term itself we want to find out. So find out that first. So what is that? Substitute. You have the expression here, substitute. So whenever you substitute that, I told you, you remove all the constant terms outside. Okay. So first I'll write the general expression. So it is 1 upon tau integration. The limits are from 0 to tau because time is t is equal to 0 to t equal to tau. So 0 to tau I naught square times t upon tau the whole square into dt. Here, what I have done, I have written the time component outside. That's it. The time component I have taken outside and I have expressed it. So first try to express it like this. This is the expression for the mean value squared. First find out this. Then you can find out the IRMS value directly, and that is the term on the left hand side. So inside term, first we are calculating. Okay. So this is there. So now go and substitute. Now we will try to simplify it further. So when you try to simplify it further, try to write the expressions. So we can take, as I said, I naught square is constant. Take it out. So I naught square. So I naught square term, I'm extracting it out. Then the t square term will remain inside. But what about the tau square? 1 by tau square, that is also constant, can be taken out. That will get multiplied with the tau outside and become tau cube. So I naught square upon tau cube times integration from 0 to tau t square into dt. This is what you will get. Okay, into t square into dt. Now, you try to differentiate. I mean, you try to integrate, sorry. So when you integrate, what happens? Integration of x power n into dx. There is a general formula which you people would be aware of. Even if you're not, you can listen now. I'll tell you. The general expression is x to the power n plus 1 upon n plus 1. Okay? Plus c, all arbitrary constant will come. Here we don't show that constant. Okay? This is the general expression. Now you go and write it. So that is equal to I naught square upon tau cube. So integration of x power n dx, as I told, x power n plus 1 upon n plus 1. So integration of t square dt would basically be t cube upon 3. That's it. So limits are from 0 to tau. That's it. Okay. So you will get it. Now final expression, upper limit minus lower limit, all that you do. Okay. So only tau term would come into picture. So you can write that as I naught square times tau cube upon the bottom also you have tau cube into 3. So the tau cube terms would get cancelled off and you will get I naught square upon 3. So we get it as I naught square upon 3. So we have now found out the term inside. So I mean term. So square term itself we have found out. How much is that? That is I naught square upon 3. Go and substitute it. So finally, you know IRMS is equal to under root of I mean the whole square. Substitute it. So under root of I naught square upon 3. Okay. So when you simplify this, I naught will come outside of the root, the square term. So you will get I naught upon root 3. So that is the expression. So this is the final answer. So the IRMS value of current is I naught upon 3. So the answer is option D actually. So D is the correct option. So that this is how you solve it. Step by step when you go to solve it, this is how you do it. Now children, because integration, is a different genre altogether. If your roots are strong in calculus, this is not going to be a big deal. Okay, I would insist all of you to practice this once. Okay, after the class you sit, you try to do it without seeing and check whether you're getting the same answer. Okay, the way I have done it. So only by practice you will get it. Okay, because it's a mathematical aspect. So math by practice only you will get. The more problems you practice, you will be benefited. All right. That's it. So this is how you solve and find out the answer for such questions. Okay, questions wherein you have calculus approach. Okay, fine. This is the third different model of question that we have solved. So these are the aspects. These are different aspects in which the questions can be asked. So three different aspects we have now covered. So with that, we will move on positively. We are going on to the next part. So what is the next area? We will see. Okay. Next, we have something called as the alternating current circuits. Different types of circuits. Now we are going to discuss. Okay. So we have something called as phasors. Phasor notation is there. So how the phasor notation is used to represent the alternating currents and voltages. Okay. And what are the different aspects? What are the output waveforms? All that we are going to see. Okay. This is a different topic altogether. So we will see it. First, trying to understand what is a phasor. So now we are going to see the phasor diagrams. and circuits. Phasor diagrams and circuits. Generally, we are going to see. Now, for that, you need to understand what is going to be, what is a phasor altogether. Okay. What is meaning of a phasor? What is the meaning of this word phasor? So we try to understand that basic term first before we get into this topic. Phasor is nothing but it is a diagram that represents. Phasor is a diagram representing, okay, which is going to representing the alternating current. Okay, okay, we'll just put it as AC, alternating current and alternating voltage. Okay, alternating current and the alternating voltage as rotating vectors. Okay, as rotating vectors. That is what is your phasor all about. Okay. Now, how do you express as rotating vectors? How we are going to, how they do it, how it is real time. Now, for this children, you need to have a visualization aspect. So I'm going to share an animation video for this because I want you guys to visualize. Okay, so when you visualize, it is easy to understand this concept. Okay, so I'll just put you on pause and I'll mute myself. Just give me a minute. I'll open a new window and I'll share the video. Okay, and you guys have to check and tell me if the audio is audible for all of you. Okay, let me put myself on mute now and then I'll get back. Yeah, so now I'm going to share it, share the, the window where the animation would be played. So I'll share it. I'll start sharing it. Okay, for that I need to start sharing this first. So I will reshare. I've started sharing my the animation window now. So I hope you guys are able to see it. Is it visible to all of you? Okay. So I started sharing. I hope you are able to see it. So I will play it now. I'll be on mute. So first go to the video. Wherever explanation is required, I will stop and I'll explain. Okay. So I will play it. I will.
We have seen that alternating voltages vary sinusoidally, and thus are represented by such an equation. Here this is the amplitude, or the peak value of voltage. And this is the angular frequency of oscillation, which is equal to 2 pi into the frequency of oscillation. Now, this equation is similar to the equation of SHM we have already studied, where we had seen that an SHM can be considered as a projection of a uniform circular motion. Similarly, we can represent alternating voltages as a projection of vector rotating anti-clockwise about origin. This is called a phasor diagram. Here length of this vector is equal to the amplitude of voltage, and it rotates about origin with constant angular velocity equal to omega. For this course, we will use the convention of using capital letters to represent the amplitude, or the peak values, or the maximum value of the sinusoidally varying quantities. And we will use small letters to represent their instantaneous or time-varying values.
Now, if you can see, in this animation video, they are showing you how phasors are used to represent the alternating current. So phasor is nothing but a rotating diagram of vectors that represents the amplitude of any given alternating current. So here you can see the arrow marks are used. So the arrow marks are nothing but the rotating vectors. The length of the arrow marks represent the magnitude. Okay, you can see V of t is small, but V naught is big. The arrow mark is big. Have you wondered why? That is because V naught is peak value. Whenever you say peak value, you know it is maximum, right? That's the reason the arrow mark is big. The arrow mark is small for just V of t. That's because it is not peak. It is just an instantaneous value. Okay. It's just a general explanation. So therefore, that is just the amplitude, normal amplitude. But when you talk about peak amplitude, then it will be more. Peak value will be more. So that is what you guys need to understand. That is what the sizes of the arrows of the vectors represents. Okay, be it voltage or be it current. So when they start rotating, now you know it is representing uniform circular motion, as they already told. So which is simple harmonic motion. It's again a harmonic function. So sine is a harmonic function, and therefore it is representing a sinusoidal waveform when it is going to originate exactly from the origin. Okay. Now when you add some phase angle to it, therefore you can see that is going to either lead or it is going to lag the voltage. Now here they have used omega t as an expression. So that is a phase angle that is present. So omega t is the phase angle. V naught is nothing but your peak value. The arrowhead is going to represent the maximum value, that is the magnitude of the given value of your AC, be it the voltage or be it the current. So when it starts rotating, you can see there is a waveform that is created. So this waveform is due to the phasors. So the basic ideas from phasors, when the phasors are being mapped on the graph, you can see the mapping will give you a sinusoidal wave. So this is how you can visualize what a phasor is ultimately. Okay, what a phasor ultimately is. Okay, I'll again unplay the video. You can see it completely. You can easily understand when you try to visualize it.
Projection of this vector on the vertical axis gives the instantaneous value of voltage. That is, it gives the equation of time varying voltage. At some point, instantaneous voltage of source is 0. Then it reaches a maximum value, with polarity in one direction, decreases back to 0, and then reaches a maximum value, with reverse polarity, and so on. Also, we will explore in this chapter that when a source of alternating voltage drives an alternating current in a circuit, then voltage and current are generally not in phase. That is, they do not achieve their maximum values at the same time, and do not become 0 at the same time. We had also discussed that when two SHMs have a phase difference, this means that their corresponding circular motions have a phase difference. If we represent this SHM by such an equation, then this SHM, which is behind the first one by a phase of phi, will be represented by this equation. If we plot these equations, then this SHM will be shifted towards right by an equivalent phase difference of phi, as this graph is in terms of time, and one cycle of 2 pi rotation is equal to time period t. So the graph of this SHM will be shifted by this amount, and it will be shifted towards right, because it will achieve its maximum value after this SHM achieves its maximum value. If this SHM was ahead by a phase of phi, then its equation will be like this. And as it achieves its maximum value before the first SHM, so its graph will be shifted towards left by an equivalent phase difference of phi. AC voltage and current in circuit have the same angular frequency, but different amplitudes, and are often out of phase. If current lags voltage by a phase of phi, then in phasor diagram, the amplitude vector of current is behind the amplitude vector of voltage by a phase of phi. And graphically, current will be shifted towards right by a phase of phi. If current leads voltage by a phase phi, then the amplitude vector of current is ahead of the amplitude vector of voltage by a phase phi. And graphically, current will be shifted towards left by a phase phi. And sometimes, when the voltage and current are in phase, they are represented like this.
Okay, so that was a video to visualize what are phasors. So you could see that whenever one of the vectors, rotating vectors, you can see that there were two arrow marks. Okay, each arrow mark represents the vector, be it the current vector or the voltage vector. All right. So if one of them is going to be ahead, you call them that you say that they lag, they are going to lead. If they are going to be behind, one another, then you say they are going to lag. Lag means one is behind the other, and leading means the one vector will be ahead of the other. Okay, so basically the vector reference is your instantaneous vector. Okay, that is your reference vector. The other vector is going to be above or below. So you can say if it is above, it is going to lead. If it's going to be below, you say it is going to lag by whatever phase angle. It can be phi, okay, or 2 phi, whatever it might be. So that is the basic idea that you try to understand from this animation. Okay, and how the sinusoidal graph is being drawn. That also they showed it. Now we'll go back to where we left off. So I'll give you the expressions for the vectors and how we are going to write them for different circuits. So now you will have an idea. You have a fair idea of how to do it. So let me go back. And now again sharing the writing pad. So where I'm annotating. So we are going back. Okay, so in this vector phasor diagram, the first part, the first circuit that we are going to discuss is AC resistor circuit. Okay, that is the first circuit. So whenever you have an AC resistor circuit, you all know resistor means this is the symbol, right? So you have a resistor that is going to be connected to an AC source. Okay, so I take a resistor. I'm connecting this to a AC supply. So the AC supply is always shown like this. This is a general, representation for an AC supply. You just put a circle and you just put a small sinusoidal wave there. It looks like a snake. So that is the AC supply. On the top, you have a resistor. So resistor has always got a resistance of R. AC supply, obviously, it is going to provide an AC voltage. In fact, that is going to create an alternating current that is going to flow in the circuit, in the external circuit. So general expression for alternating voltage by the AC source is V is equal to V naught sine omega t. Okay, that is the general expression. Now, having understood the components of the basic, AC resistor circuit, what we do, we are going to write down what is the expressions for the current and voltage, all that we do. Okay, so again here, because it's just one loop, we try to apply from current electricity chapter, you would have learned how to apply the Kirchhoff's loop law. Okay, you apply the Kirchhoff's loop law here. Okay, it tells you that the potential difference inside a closed loop is equal to zero. Okay, so I apply the Kirchhoff's loop law. So from that, I understand that the potential difference across all the components inside the loop is zero. So using that information, I will get V naught sine omega t, okay, is equal to I. The current flowing through this, we can call it I, generalizing, is equal to I into R. So we express it like this. Okay, simple. So when you write this, so now if you want to go for a rearrangement, also you can go for a rearrangement. You can find out what is current I. So I is nothing but V naught upon R times sine omega t. This is rearranging. You know V naught by R is nothing but I naught, isn't it? So I is nothing but I naught sine omega t. Simple. So like this, we have got the expression for current, alternating current. Given the expression of alternating voltage, we have got a relationship. Okay, this is your current expression. Voltage expression, already it is known to us because that is the voltage supply. Okay, AC voltage supply. That's it. So both the expressions are there. Now let me mark the expressions as 1 and 2. We try to now represent these both current and voltage as phasors. That means as vectors we are going to express. So when you try to express as vectors, take the quadrant. Okay, I am drawing the quadrant here. Okay, that is your x and y axis, both I am showing. Now, when I'm going to express the voltage expression, say V is equal to V naught sine omega t, always I'm going to express the amplitude of it. What do you mean by amplitude? Peak value. What is the peak value of the voltage? V naught. So that is what I'm going to express. So I will express using arrow mark like this. So this is V naught, I will say. Next, coming to the current. Now, when I talk about current, you can see for current, I is nothing but V naught by R, right? So V naught divided by R sine omega t, which is your I naught. So therefore, your current amplitude I naught will be smaller. It is not going to be bigger. Its magnitude is less. So therefore, I am drawing it smaller. And I am overlapping it over your voltage itself. Why am I overlapping? That is because both of them have no phase difference between them. Both of them, it is omega t only. It is not different. So that is the reason it is the same. Okay. So we are not overlapping because there is no phase difference between them. It is not plus pi or minus pi, or there is no plus or minus term. So therefore, we are overlapping and we are trying to show it. Okay. So that is what we are not showing. We are not, displacing them by any angle. It is overlapped. If it's been overlapped, you know that the angle is going to be 0. Okay, so that's the reason it is overlapping and we are trying to show it. So here, neither current nor voltage is going to lag or lead. Okay, none of them are lagging or none of them are leading. Both of them are having the same, this one, phase difference. Phase difference is not at all there here. Okay, it's constant. So that is the reason it is going to be 0. Okay, so you understand that. Yeah, that's it, student. So this is the basic thing. So for the first circuit, we have now shown. We have written the expressions, we have applied the Kirchhoff's law, and we have shown the phasor notation. The general notation we have shown. Okay. Now this is the phasor notation. Now when you draw it as a circle, simple harmonic motion, if you want to show it, you know that it's a rotating vector. So you will get 2 concentric circles. One small circle, one more is a big circle. Okay, having a larger radius. That's it. So it will look like this when you complete the diagram. Now when you map the waveforms will be different. Okay, so when you draw the waveforms, then one by one you should draw. First for voltage and then you can draw it for current. Now voltage, obviously it is a sinusoidal waveform. It will look like this. Okay. So I'm using this color, orange color. So this is basically your peak value of voltage on the top. So V naught, and here there is a negative peak. So that is anyways going to be minus V naught. You guys know that, right? So like this you represent, because V is equal to V naught sine omega t. Same way, if I want to show for current, current I is equal to I naught sine omega t. But we know that I naught is less than V naught. That is the reason if you're going to show the current waveform, that will be smaller than your voltage waveform. No doubt both will have the common point of origin. But look at this. This is how it is. So when you try to map it, so this is your I naught peak value, and this is the negative peak, and this is the positive peak. Negative peak at the bottom, positive peak at the top. See, this is how you show it. There is no phase difference as such. That's why they have a common point of origin. You understand? This is the waveforms. So coming to the time period, you know that this is one complete time period. So t in between it is half t by 2. Here is the origin, it starts, so 0. Okay. So like this you can show. And generally, when you say phasor, it is representing a complete rotation. So one complete rotation in terms of radians also we show it. Okay. So when I show in terms of radians, then I will remove the t. I will express in terms of pi. Okay. So in terms of pi. So how do I express? First is 0, then half of it here in between the waveform. So I will represent as pi by 2. Here it is going to be pi, then 3 pi by 2. Finally, it is 2 pi. So like this, you will express it. Okay. So 0 to 2 pi, 2 pi radians is, 360 degrees, right? One complete rotation. So using that logic, we are going to express it. Okay. So this is how we go for a waveform. Output waveform of when AC voltage is applied for a resistor. This is how the output waveform of current and voltage would look like. Okay. So now we have had a detailed, analogy of current and voltage for AC circuit, AC resistive circuit we have seen. Same way we have AC inductive circuit, and we also have AC capacitive circuit, combinations of inductor and capacitor, capacitor and resistor, resistor and inductor. Then all three also will come. LCR, okay, inductor, capacitor and resistor. So all that we are yet to see. All right, so we have seen the first part. Okay, AC resistive circuit we have analyzed today in this lecture. Fine. So I don't want to burden with a lot. So first, please go through this. Okay. So try to grasp the concepts taught in today's session. Go through it, and then you have any doubts, please ask, because definitely you will have doubts. This is not an easier topic. This is a little complicated. Okay, because we have calculus part coming in, and there are different functions. So therefore, it's better that you go through it. If you have any doubt, please try to discuss it immediately in the next lecture and get it clarified. Okay. So with this, we'll wind up. Okay. You have any doubts, children, in today's lecture? Also, you can ask. Yeah.
Okay, thank you, Manish. இங்கே இந்த டிரான்ஸ்கிரிப்ட் எல்லாம் கேன் யூ சென்ட் இட் yesterday's class and today's class?
Yes, sure. I'll send
Because
it.
these people, if they want to go through it,
Definitely,
easier for
definitely.
them. I suggest for
Yeah.
the students லீவ் இருக்கும்போதே இந்த டிரான்ஸ்கிரிப்ட்லாம் ஒரு தடவை இங்கெல்லாம் டவுட் இருக்குது அதெல்லாம் கொஞ்சம் படிச்சிருங்க. எல்லாம் தரவாக இப்போ இதெல்லாம் ரொம்ப பேசிக் திங் தான் சொன்ன மாதிரி எனக்கு தோணுது. எல்லாம் தரவாக இருந்தால் பிரச்சனை இல்லை. தரவு இல்லைன்னா யூ ஜஸ்ட் கோ த்ரூ இட் ஒன்ஸ் அகெயின் அண்ட் தட் பேசிக் ஃபண்டமெண்டல்ஸ் அதில் டச் பண்ணியிருக்காருன்னு நினைக்கிறேன் இன்றைக்கி. I think you should be very 100% clear on these fundamentals. அது ரொம்ப முக்கியம். Am I correct, Manish? You have touched the fundamental pi by 2, pi 3,
Yes,
pi by
yes.
2, and how do they get the
ஆமா.
sinusoidal? All those stuff. No, that over
Yes.
that omega நம்ம W மாதிரி போட்டிருக்காது. Whatever.
ஆமா.
So how
Annular
do we get
frequency.
it? And no 2 pi something என்னமோ போடுறாரு. So all these things, no, you have to be 100% confident இருக்கணும். அந்த கான்செப்சுவல் அண்டர்ஸ்டாண்டிங் இருக்கணும். சும்மா மொட்டையாக நமக்கு ஏதோ அது போட்டோம் அப்படின்னு இருக்கக்கூடாது. How did we get it? அப்படிங்கிற மாதிரி இருக்கணும். Anyway, I think you will be doing it because that will help you in your exams. That is the point. And understand பண்ணி படிக்கிறது பெரிய அட்வான்டேஜ் அதுதான். Okay, thank you students. I think it's almost 9 o'clock ஆக போகுது. Yeah. So for your patience.
Thank you, sir.
சொல்லுங்க மனிஷ்.
Okay. Yeah. இல்ல uncle, நான் ஒண்ணும் சொல்லல.
Yeah, anybody wants to say something?
Somebody was telling something.
Yeah.
You have any doubts? You can ask. No worries. That's it. I hope you can go through. Only once you go
send
through
the
and read,
doubts
you
in
will
the
have
group
doubts.
also. In case you are not able to spell out now, you can send the doubts in the
You can
group.
put it in the group. Yeah.
Yeah, that's very important. Okay. Okay. Thank you, Pa. Thank you.
Okay. Yeah. Welcome, children. Bye-bye.